the organizers for really an honor to participate in this tribute to Mike. And I'd like to talk about this ongoing joint project with Jim Conant and Peter Teichner. And really the origins of this project go back to some ideas of Mike in the late 70s. In particular, there's a paper with Rob Kirby on the geometric proof of Rocklin's theorem. And in the book with Frank Quinn, the generalized Cabrera-Milner invariance, where you count intersections between Whitney disks and immersed spheres. So, we really got inspired by that and have been trying to push this further. So I'll try to explain this picture roughly, and I'm not going to have time to go through that many details. My son helped me prepare outlines, which is roughly start here, and then we're going to miss all the good parts, all the techniques that you use to climb up higher, and we'll jump up here. Okay, so I'll start with some basic examples, and hopefully this will be enough to, absorb the gist of the formal definitions, which I will probably skip over pretty quickly. Okay, so starting at the bottom, linking numbers can be thought of as order zero intersection invariance. And I just want to set the notation here. On the left, we see the Hopf link in the boundary of the four-ball. So the arrows from left to right indicate moving into B4 in the collar of the three-sphere. So I'll stick to that convention. So what we see is that one of the components gets, so the arrow indicates sort of a product extension into the four-ball. Then one of the components gets capped off by a disk here. That's so this D1 refers to the disk you see extended back to the boundary. So that's the capping off, and then of course you get one intersection point with a disk described as bounding the other component, which then extends a little further into the four-ball and gets capped off by another disk. Okay, so this is hopefully a familiar picture, and it's very nice the way among all the different formulations of linking numbers, there's this simple picture where you can intersect some disks bounded by the link components. And of course, they don't have to be embedded, but this is the easiest example of a Whitney tower. And the order zero refers to the fact that there's zero Whitney disks around. Okay, so then when we have vanishing linking numbers, then we can build an order one linking tower. So again, on the left we see the Baromean ring sitting in S3, the boundary of B4, and moving in, as before, we cap off one component with this disk. So this D1 is extended in the collar all the way back into S3. And this has a canceling pair of intersections with the disk bounding the second component, which of course extends all the way a little further into B4 and then gets capped off by a disk here. And so we see this canceling pair of intersections admitting a Whitney disk. And since we're just absorbing the ideas here, we'll just look at the picture, see that it has a transverse intersection with the disk bounding the third component, and just note that this is an example of a Whitney tower. And it has order one, which refers to the fact that there's sort of one layer of Whitney disks around. And this transverse intersection between the Whitney disk and another disk is an order one intersection point, and we can associate an order one tree to such an intersection point. So again, this tree can be, sits right inside the Whitney disk. So this is the same picture as before with some of the labels removed. And this is an example of an order 1 intersection invariant. So, some of you probably are familiar with computing the triple linking number this way. So again, the Whitney tower was the disks bounded by the link components, and then together with this one Whitney disk, and we associated an order 1 tree to that intersection point. And so it looks like this. The labels kind of come from the disks that are sitting at the end of the edges, and that lives in some group. So there's indeterminacy here, and a lot of what I'll try to talk about is explaining the relations that you need in order to make such an invariant well defined, so that it only depends on, say, the boundary.
Sorry, Rob, could you explain how the tree is drawn?
How the tree is drawn?
Yeah.
Okay, so we have a Whitney disk here, and let me go back to frame. Okay, so are we okay with this picture?
Yep.
So this Whitney disk pairs the disk bounded by the first component and the disk, intersections between disk 1 and disk 2. And then it has a transverse intersection with disk 3 in its interior. So you can think of putting a base point in the middle of the Whitney disk, and then there's sort of 2 directions downward. You can go to one boundary arc that lies on disk 1. You can go to one boundary arc that lies on disk 2. And then you can go up to the transverse intersection point.
So the second arc lies on the ends on the boundary of this two, or this picture is at a depth into the four ball, so it's still in the interior?
Okay, so yeah, this is sitting in the interior of the 4 ball, and now the labels 1, 2, and 3, they're in the picture. They're at the end, at the univalent vertices of this tree. Now they could extend to, let's say, base points in each of the disks, but that information is not important at the moment. Let's see. You can just literally take, whenever you have a Whitney disk, you can just, in this picture, just leave the tree in the Whitney disk. There's 2 boundary arcs going down, that's the 1 and the 2, and then there's this intersection that we think of as going up, and those are your 3 univalent vertices. Okay.
Well,
Yeah.
you got 2 or 3 aiming on the actual circles in the original links.
No. So we're pushing into the 4 ball here. So these arrows, remember the convention. The left side is S3 boundary B4. The arrows indicate pushing into B4. Okay, so we have the Hops link here. And now if you just forget about the Whitney disk, this component bounds a disk where you move in by a product, then you cap it off with this disk. The second component bounds a disk where you move in by a product, and then say cap it off here. And this top component bounds a disk where you move in by a product. After you cap this off, then you can just cap this off a little further in, or make the disk bend around a little bit. Okay, so this is like a moving into B4. And then all the action happens in the Whitney disk, where this is a simple link, so we're able to put the entire Whitney disk embedded in one slice of S3 cross I as we're pushing in collar into B4. So any other questions? You okay with that?
Are you going to do one more example?
Yeah, one more example. Okay, so now we have a link on the left here. This is big double of the Hops link. So it has vanishing linking numbers and vanishing order 1 intersections. So we can build an order 2 Whitney tower. So So it's the same convention where the arrow means pushing into B4. We move in a little bit and we cap off the first component with this embedded disk. It hits the second component. This is not the second component of the link. This is, we're extending these components inward by a product. So this is, this second component of the link really is a, part of the disk bounded by the second component as we move into the four ball. And we get these two transverse intersections that support, that emit a wiki disk as before. That wiki disk intersects the disk bounded by the third component in the canceling pair. And we do the same thing, put in a wiki disk for that guy. And now that has a transverse, that wiki disk has a transverse intersection with the disk bounded by the fourth component. And so this is an example of an order 2 wiki tower. And we can associate a tree to this unpaired intersection point just as before. And now you hopefully can see the idea of associating trees to points in the tower, intersection points. You start at the point and you just start flowing down. At each wiki disk you bifurcate because you have a wiki disk pairs 2 lower order disks. So then if you keep going to another wiki disk, you split again and bifurcate and you get this unit trivalent tree. Yeah.
So that was my question, because in this right-hand picture there,
Yeah.
you have that bottom part running out and touching the original circle that we want.
Well, so
Or it's pushing.
yeah, so it doesn't matter. So you can either extend this all the way back to, let's say, a base point on the link. It's a univalent edge of the tree. So, yeah.
In this picture, it touches the circle that we want pushing it, whereas the previous one, you left out that arc. That's my question. Yes.
Oh, I see.
That's my question. Should that arc be there or not?
Doesn't matter. But you're right, though. I should have maybe put that arc there just because maybe a more, yeah. The trouble is that then you would also be extending this arc, which is harder to draw, maybe back to, well.
But it's just a point in the disk. It's not a point on right? It's in the tree's in the wiki disk until it hits the actual.
But yeah, Rob's right, though. I should have drawn this extending because in the iterated picture, you see that you go down to the next level, and then if there's a disk there, then you're going to keep going along till you get to some base point in the disk, and then that splits again. So what's real, this is drawn correctly, and what you don't see is that this actually, continues into that disk as well somewhere. All these endpoints that are labeled, then you go into some base point on the disk bounded by these components. Okay, but the main point is that's sort of a minor detail. You build up these towers of disks, you have an intersection point, and to get the tree, you go down bifurcating, and it describes a trivalent tree. And so the question is, how do we count these guys in a way that's well defined? So describing the relations is the challenge. Okay, so this generalizes to order n wiki towers in the four ball, and this also, it's an example of 3.5 dimensional topology in that these towers can be defined in all kinds of four manifolds, and I'll just stick to B4 and just talk about links in the boundary of the four ball bounding wiki towers. Okay, so with that in mind, we have this construction theorem where if we have a wiki tower bounded by a link, we can define an invariant, and that's this tau infinity here, or twisted tau that counts trees in some meaningful way, so that if it vanishes, then you can build the next order tower bounded by the link. So we have this obstruction theory that works. And of course the trick is, where does this zero live? It's some abelian group that I will describe to you in detail. And then to detect obstructions to the existence of the towers, we're going to use Milnor invariance of the link, and it'll point, and also the classical ARF invariant, and it'll point towards some new higher order invariance. So again, the point here is that we define this combinatorial intersection invariant that we can identify with some algebraic invariant, but this combinatorial guy can be defined in much more general settings, like for inverse surfaces and four manifolds. You don't need a link complement around. And if you don't know what Milnor invariants are, it's not so important at this point, and I'll be able to say a little bit about them, but they're concordance invariants of the link. And then we can actually classify these guys in the four-ball. So we look at the set of links bounding order n twisted Whitney towers, modulo order n plus 1 Whitney tower concordance, and you get abelian groups, which are finitely generated, and we'll give a classification of these. So in particular, in 3 out of 4 cases, we get these free abelian groups of known rank. So this n sub n is the number of independent Milnor invariants. So it's a known number, and
Are you talking about mu and bar?
so these are first non-vanishing Milnor invariants. So there's no indeterminacy in the Milnor invariants.
But what about repeated indices?
Oh yeah, you can have repeated indices, yeah, right. And then in the remaining quarter of the cases, that's where there's some torsion that shows up. And in the lowest order, that's the classical ARF invariance of the links. And in the higher orders, we'll formulate some new invariants, and they live in the quotient of the Freely algebra on a certain number of generators that corresponds to the number of components of the link, tensor with Z2, and modulo some as of yet unknown subgroup. So it's possible that these new guys are trivial, but we don't believe they are. And in any case, we can precisely formulate the map from links into this this group, and it's the only possible remaining obstructions to this, to whether a link is 0 in this group or not. Okay, so I'll try to describe, skipping a lot of details, this program as it exists. Yeah.
Just check, the word twisted means that there's no framing condition on the disk.
Right. So I'll explain the word twisted. So, we're talking about Whitney towers, and I'll explain the Whitney move a little bit and Whitney disk, but there's this framing issue that sort of is subtle, but actually gives a lot of the special flavor. So, okay, the general picture associating trees to Whitney disks and intersections has the mantra that Whitney disks correspond to rooted trees, and transverse intersections, which are not paired by Whitney disks, correspond to unrooted trees. So if you look at the picture on the left, we have some Whitney disk here pairing a red sheet and a blue sheet, and the red and blue, are labeled by W, so they could well be higher order Whitney disks already, and so we're getting a yet higher order Whitney disk that's pairing them. And as I said before, the corresponding tree sort of bifurcates down. And the reason it's rooted is that, well, nothing's intersecting this Whitney disk necessarily, and we just put the base point somewhere in the interior. And if something does intersect this Whitney disk, well, then we hook on that base point to that intersection point. And similarly for this Whitney disk, and so we actually glue the roots together. That's what this operation here, you're gluing the roots together, a Whitney disk labeled by this guy and this guy. So you get an unrooted tree. unrooted trees, that's sort of like commutators and unpaired intersections, you glue the roots together so to get an unrooted tree. Okay, so then the grading of everything in sight corresponds to the number of trivalent vertices in the trees. Okay, so that's by definition for trees, and then we have trees associated to our Whitney discs and intersections, so that tells us what order they are. And so to define Whitney towers more precisely, you do it inductively. So you start at the bottom, you have properly immersed surfaces properly immersed discs in V4, and that's the Whitney tower of order 0. And you pair up intersections by Whitney discs as high as you can go, inductively, layer by layer. So in general, it can be, quite messy, and it turns out that you can clean things up and get a handle on what's going on by using trees. Okay, so we want to, define this invariant that will count the trees in a way that when we get 0, we know we can build the next order tower. And so there's a couple of well-known relations in these tree groups that show up, namely the anti-symmetry and this IHX Jacobi relation. So the way you interpret these pictures are, well, there's orientations on the trees that are, cyclic around the trivalent vertices, and you can think of it as orientations as coming from an orientation on the plane. So in particular, in the first equation, the trivalent vertex, the orientation has been reversed. But these univalent vertices extend to fixed trees. So in other words, the tree that goes off here is the same as the tree that goes off there. So these are local pictures. And the same for this IHX relation, which behaves like a Jacobi relation. It's analogous to Jacobi relation. So, these univalent vertices are, a fixed tree here, fixed tree there, fixed tree there. And then, if we take an order n Whitney tower and, add up all the order n trees we see with, again, I'm ignoring the orientation conventions, but you can get a sign here just like the usual intersection number between surfaces in a four manifold, and you take this sum and interpret it in this tree group modulo the anti-symmetry and the IHX relations, and that's your order n intersection invariant. And if it vanishes, then you can build the next order Whitney tower. So what's going on with this obstruction theory is that the link is bound in some immersed disks, and then we're building higher, choosing higher Whitney disks. What we really care about is information about these order 0 disks. Can they be moved to be disjointly embedded? So is the link sliced in the four ball? So going back to this this idea of building the higher order tower is supposed to be a better approximation to finding sliced disks. And the proof of this is done by realizing all the relations in this target group. So the main one is this Jacobi relation, Jacobi identity, the IHX relation. And you can actually manipulate the Whitney tower by looking at the trees and arrange for everything to cancel, and so you build your next order tower. And one of the main tricks is that if you're given a Whitney tower with all these trees sitting in it, you can clean it up by, let's say, doing a finger move where you push down and split this disc into 2 to separate the trees, and then you can split this Whitney disc further, and so you get all the singularities in the Whitney tower are contained in thickenings of complete control over lots of aspects, you know, to realize the relations. Okay, so, you know, a lot of the moves you use are actually Whitney moves, and if all your Whitney disks were embedded and free of interior intersections, you could actually undo all the singularities and find some slice disks at the bottom. So here's a model of Whitney move. So again, we have blue and red sheets intersecting in 4 space, paired by Whitney disk, and this Whitney disk guides this motion of the blue sheet off of the red sheet to eliminate this pair of intersections. And so the part of the special flavor of Whitney disks and Whitney towers is that, you know, in order to pull off this move, you need a framing condition that's a little bit subtle. So, you know, there's a canonical normal section of the Whitney disk over its boundary. So I drew it here in dotted lines. So you push, you know, the boundary of the Whitney disk tangentially in one sheet and then normally in the other sheet. And if this extends to a north vanishing section over the whole Whitney disk, then you see how that gives you this this motion of the blue sheet that eliminates the original intersections without creating any new ones. So without this, you know, normal framing condition, you know, when you push off these parallel copies of the Whitney disk, so you're really adding 2 copies of this Whitney disk to the blue sheet here. You know, without the normal framing condition requirement, then those guys might intersect each other. So here's an example where the Whitney disk is twisted. So, you know, to Whitney disk, you can look at the obstruction to extending this Whitney section across the disk, and you know, you get a relative Euler number. And in this example, again, pushing into the 4 ball, we have this sort of twice twisted big double of the unknot. And so, you know, when we cap off this sort of twisted band with the disk, so that bounds the first component, we see a boundary of a Whitney disk here. And then as we push in further, you know, this capped off part disappears, and we see the rest of the Whitney disk here. And now this Whitney disk, the interior is disjoint from, you know, the red and blue disks, but it can't be used to do a successful Whitney move, because when we look at the Whitney framing here, we got this Whitney section, and it ends up, you know, not extending to a non-vanishing section over W. You can, you know, read the linking here between the section over the boundary and, you know, color of the Whitney disk. And that's telling you that this is a 2 twisted Whitney disk. So the idea of a framed Whitney disk where you can do a successful Whitney move corresponds to 0 twisted. Okay, so this twisting is going to be important for the obstruction theory. So we're going to transfer the idea of counting intersections in the interiors of disks to also counting twistings in Whitney disks. And so we again assign trees. Now remember, a Whitney disk has a rooted tree associated to it. So when we have a rooted tree associated to a twisted Whitney disk, we're going to indicate that by putting a little twist symbol at the root. Okay, so this twist is represented by that symbol. And, you know, I didn't say it before, but originally when we started building Whitney towers, we assumed the Whitney disks had to be framed because that's what we wanted to use to undo everything and get our embeddings. So if you allow some to be twisted, well, we'll call that a twisted Whitney tower. And the key idea is when you're measuring obstructions, any twisted Whitney disks, the obstructions they give will be in twice their order. So that's what we're going to measure. And I won't give a precise definition of the order of a twisted Whitney tower at the moment. But, clear from the next definition. So we want a target for our intersection invariant that we're going to apply to twisted Whitney towers. And so we'll denote this by T with this twist symbol as a superscript. And in the odd case, we have this group of trees, modulo antisymmetry, and IHX. Now we're going to throw in an additional relation. And this corresponds to a well-known geometric move called boundary twisting, which changes twisting of a Whitney disk at the cost of creating an intersection with a tree like this. So I'm not going to talk about that at the moment, but if you're familiar with that move, you can easily see that that's a clear geometric correspondence. And now the more interesting twisted groups are in the even orders. So remember, the twisted Whitney disk of order K shows up as an obstruction in order 2K. So in this group, we throw in these twisted trees as new generators, and we get these new relations. So a few words about the relations. If you change the orientation of a twisted Whitney disk, you don't change the twisting obstruction because these Euler numbers are invariant under orientation change of the disk. They're self-intersection numbers. And then this relation here, so this I, H, and X stands for the old IHX relation. So this I is actually the sum of H and X. So you can kind of see how this resembles a quadratic form where the self-intersection of the sum equals the sum of the self-intersections plus this error term that comes from the pairing. And then similarly we have this interior twist relation where this corresponds to a geometric move where when you create interior intersections in the disk, it changes the twisting by 2, plus or minus 2. And in fact, there's a precise sense in which this twisted even order group is really a universal quadratic refinement of this untwisted guy. So, question?
Maybe you said this and I missed it, but this is just a definition, but you're distinguishing even and odd cases.
Right.
Why?
So it goes back to, part of it is convention, but when you have a twisted Whitney disk, as far as the obstruction theory goes, it puts an obstruction in twice its order. So, the even orders is where where these obstructions are going to show up. And that's not obvious. Where it comes from is that once you look at the correspondence with Milnor invariants, those are, commutators, determined by the boundaries of these Whitney towers. So if you take the longitude of a link, it represents some commutator in the meridians. And you can read it off from the Whitney tower. Whenever you get to a twisted Whitney disk, there's this reflection of the commutator back down the tree, so it doubles the length of the commutator. That's the short answer. So it might show up a little later. Okay, so all of this stuff that, yeah, Mike?
So I'm not sure I understand the bracket. I thought that was some kind of concatenation of trees.
Okay, no, the bracket is where you glue the roots together. So
then you get something with, just roots, you just connect roots.
right, so this, these capitals represent some Whitney disks. And this bracket pairing is where you have actually an intersection between them, transverse intersection. So you glue the roots together. So this is an unrooted tree here. This is a rooted tree labeled by, the twist symbol.
Yeah, I was worried about that one, the left.
This one?
Yeah, so the boundary conditions are the same in all terms, that there are 4 endpoints on the boundary of this.
Right, so this, this represents the I, H, and X trees, and that have 4 endpoints,
Yeah.
and those endpoints are fixed trees throughout the equation.
Yeah, so how's that last term work?
This term,
Yeah.
well,
So
remember these, so we're putting in order n twisted trees rooted border end guys that represent, that have twists.
So the roots are not inside this disc. Is this no longer a local formula?
No, it is local, yeah.
But the root is not present inside the disc diagram, correct?
So, yeah, the root is there. I mean, you can think of these as living in the Whitney Tower itself. Yeah.
But I think what you're saying is IHX, the root's kind of far away from the IHX.
Well, it could be right there. It's just on some univalent vertex.
I guess I'm not understanding how the boundary conditions are preserved under the building of this, these 2 points.
So maybe I should draw a picture. So here's the IHX relation. Okay, so let's say this guy is labeled by the twist. So we're looking at, so this is some tree, this goes off to some tree, this goes off to some tree. Okay, so yeah, I should have made more room here. This is gonna be, let me just draw an extra tree. So now we're gonna, this error term here is glue this guy to this guy along the twist. So I might mess up the orientations, but let's see. So this has a twist there, it's getting glued onto there. So that's gonna pair with B. So I may have messed up the orientations, but this is that pairing.
Yeah, but what if that twist is much farther away? It's not that one in 4 corners.
Pardon me?
What if that twist is not at one of the 4 corners, but much farther away?
Well, then just replace this with a tree that has a twist in it.
And then the concatenation happens far away.
Pardon me?
And then the concatenation happens far away.
Right, you glue this, I mean, then you just, so this is some tree that has a, twist somewhere, and now you glue these guys.
Yeah, but that's what I was worried about. It doesn't look like a local formula. In other words, the error term with the brackets seems to have a different character because it's not just the 4 boundary conditions as the other 2 terms.
That's true.
That's true. That's true, and I should work or what?
This is an order 2n unrooted tree. I mean, I'm not sure what you mean by not local.
Well, it doesn't have the formula. At the beginning of the talk, you emphasized that IHX was a scheme relation, and now this new modified IHX is not a scheme relation. But it does make this fine. I just trying to understand the meaning of this.
Okay. Okay, so we have this mysterious group, which we actually compute, so at least as far as its group structure, I can tell you exactly what it is in a minute. What all those relations boil down to. Okay, so we have some twisted Whitney Tower border N, and now the new version of the invariant is we count the trees associated to unpaired intersections as before, and then we also count the twistings, and so for any this sum is over all the Whitney disks, but the only ones with non-trivial twisting will show up, and they'll contribute these twisted trees.
So, Rob,
Yeah.
just to follow up, so is there a geometric name for this relation?
Yeah, there is. So here this is some twisted tree in a Whitney tower, and this twist is sitting in the interior of a Whitney disk. So maybe I should have done this. So okay, so here's a Whitney disk sitting in a Whitney tower. It could be high up. So you have this tree that So we're somewhere in Whitney Tower, we see this twisted Whitney disk, and if we do a Whitney move on an adjacent Whitney disk, so here, we use this is an untwisted guy, and we do a Whitney move here and push this up. We're gonna, create some more intersections, but when we clean it all up, we'll get, this guy will split apart, and that's what will give, two turns here, and when you split that twisted Whitney disk apart, it intersects itself, and it gives you this term here. So that's a short version. Oh yeah, I was about to say, so, all of this stuff is available in a sequence, a recent batch of papers that we put on the archive. So, there's tons of details there that I can only hint at now. Okay, so in this group, we have this twisted intersection variant, and we have the analogous theorem where, if it's zero, we can build the next order Whitney tower. Now, again, it's the same idea where you realize the relations as before, everything's localized near the trees, and you can do all these moves. And the new wrinkle is that we have some of these twisted Whitney disks lying around, and they may have one way over here, but if their tree shape is the same, and they're each, let's say, you've got a +1 twisted and a -1 twisted, there's actually a way to figure out how to pair them up so that you can turn them into a framed Whitney disk. And you only do that at the cost of creating higher order stuff. So you can cancel these twisted Whitney disks if they have opposite twistings. So that was sort of a new wrinkle in that to get this theorem to work. Okay, so the motivation for introducing all this idea of keeping track of the twistings is that, as we were trying to understand these invariants as obstructions, very subtle relations started coming up, and they were best characterized by keeping track of the twistings. So again, that's something that's really hard to convey in a short amount of time, but so now we'll be able to give some nice clean statements about what you get when you look at the set of links that bound these order n twisted Whitney towers. So first of all, they filter the set of all links. So any link bound in order 0 twisted Whitney tower, that's just a bunch of immersed disks. And then this filtration also factors through concordance because embeddings are Whitney towers of arbitrary order. And when we work modulo, concordance, which is order n twisted Whitney tower concordance, that means your links are connected by immersed annuli that support an order n+1 twisted Whitney tower. Then we actually get this group structure. So the band sum on links, which is usually not well defined, for instance, up to concordance, works in this setting roughly because, when you really the links in this set are determined, as elements in this group, they're determined by their intersection invariant. And so if you have two different links and you connect it by bands, well, separately they bound Whitney towers that represent certain group elements. Well, the band sum, you just snip the bands and you get sort of the sum of the Whitney towers bounded by the band sum. So it's forms a group, and it's bound from above by the tree groups, which are finitely generated. So the goal is to compute these geometric groups here, so these groups of links. And we'll use the Milnor invariants, which are algebraic, and then this will point to these potentially interesting higher order arc invariants. Okay, so we want to use these Milnor invariants to show that these intersection numbers are really well defined. And so Milner invariance, roughly, you look at a link in S3, and you could think of it as, well, assume that the longitudes lie in, in the lower central series up to some level of the link group, and then you just read off the commutators you get for each longitude. And those turn out to be concordance obstructions. So we want to use the correspondence between commutators and rooted trees to describe this invariant. So that's why we're going to define the free Z-Lie algebra on M generators. So this M corresponds to the number of components of the link. And just remember, a rooted tree corresponds to a commutator by this picture. So remember, there's orientations here. That's where you get the ordering of the components in the commutator. And then recursively, you get, iterated commutators. And, as an abelian group, this is just, if you look at the, degree n part of the Freedman algebra, it's just order n minus 1 rooted trees modulo IHX. And instead of antisymmetry, we have this stronger self-annihilation relation. Okay, so the trick to get from this, twisted intersection invariant to the Milner invariance is we have to get from these unrooted trees into these rooted trees. And this really nice map, which is sort of the obvious one, sums over all choices of a root. So, here's an example. If you have this unrooted tree, you just, one by one choose roots. And this first entry is just a bookkeeping. That's like saying, well, we're looking at the first longitude, and it represents this commutator in the other meridians. And go all the way around the tree, you get expressions like this. So for another example, again, this has an order 2 symmetry, so you end up just doubling this expression here. And for the twisted trees, well, they're already rooted, but as I said before, they really represent obstructions in twice the order. And so this map on those guys, you take a rooted tree and you glue it to itself, compare it to itself along its root, and then apply the previous formula and divide by 2. So again, this comes from just fundamental group computations in the link complement, more or less. What corresponds to that? Okay, so it turns out that the image of this map we just looked at, lies in the kernel of the bracket map to the next degree of the Freedman algebra. So, and this is this, free abelian group of known rank, and we'll denote it by d sub n. And the theorem is that, this map computes the Milner invariance of the link. So first you take the intersection number in the tree group, then you apply the map, and it gives you this first non-vanishing Milner invariant of the boundary of the Whitman tower. So, this kind of relation between Milner invariants and things like Whitman towers was actually, known in various versions for quite a while, but I think this is the first time that this explicit map and sort of the explanation for it was discovered. And, again, I can only say briefly the idea, but it's really summed up by this picture. So remember we saw this link before, and it has this is an order 2 Whitman tower. And so just look at the first link component. If we resolve this Whitney tower to a growth where that's bound, where you see this class 3 growth bounded by the first link component, it turns out that you can read off the longitude by just looking at this growth. So you have, a commutator of, the second meridian to the second guy with this boundary of this stage of the growth, and then that's also a commutator in the other meridians. So, this map, the geometric map going from Whitney Towers to Groves corresponds to this algebraic eta map where we, chose routes at all the univariate vertices. And what's amazing is that there's a dual picture here. So you only need to do this resolution once, and you can also read off the longitudes of the other link components in the same picture, because, look at this fourth component. What we see here is, what used to be a Whitney disk transversely intersecting what is a disk bounded by the fourth link component. So a meridian to this, a normal circle to this Whitney disk is contributing to the longitude of the fourth link component. And by growth duality, that then can be written as a commutator, going down in following the rest of the tree. So again, can't explain that better than that for the moment, but this geometric map is really the explanation of why the Milner invariance can be read off this way. And so now we're close to computing these groups of the links that bound order and twisted Whitney towers, because the algebra we finished. So in other words, this theorem shows that for 3 out of 4 cases, this tree group, twisted tree group, is isomorphic to that target of the Milner invariance. So that's this bracket kernel. And the proof of this uses some little bit tricky, uses discrete Morse theory on chain complexes with torsion, and it really was inspired by Jerry Levine's work, where he actually, conjectured this theorem in a different version and worked on it. It's related to homology cylinders in dimension 3 and string links, and he made progress on this and came up with an extension of the Hall basis algorithm to what are called free quasi-Lie algebras, where you have anti-symmetry instead of self-annihilation. And so using this result, then right away in 3 out of the 4 cases we get the classification. And that's because basically the eta map factors through a map from the trees straight into the, you realize trees as links, and then you take Milner invariance. So you get that all 3 of these groups are isomorphic in this case. And then the remaining case is the hard one. So this is where the higher order ARF invariants come up. And so we'll define these guys on the kernel of the Milner invariance in these orders 2 mod 4. Okay, so again, the algebra is all worked out. So we know that these tricky groups fit into this exact sequence. And the question is it short exact? So so the only, possible remaining obstructions to computing this group, lie in whatever the inverse of this map is. So we can define, at least modulo the kernel of this alpha map, these higher order ARF invariants. And, from all the algebra that's worked out, we get the result that, these are the only possible remaining obstructions. So in all orders, the groups are classified by Milner invariance together with this special case in the 2 mod 4. And the remaining question is, are these ARF invariants non-trivial? And so at the bottom, they correspond exactly to classical R invariants. So we know that there's two torsion. And, you know, this map that goes from, you know, the Freely algebra mod 2 into the group of links, you know, explicitly, you take a commutator written as a rooted tree and you double it. Well, you pair it with itself sort of as a commutator, and those are the possible rooted trees that will realize these higher order invariants. And we know how to construct links with this invariant. So we conjecture that all these guys are non-trivial. So in other words, that this map alpha is injective. And so, you know, all the links that correspond to these trees here, these twisted trees, should be, you know, new, you know, examples of links that don't lie in the next order of the filtration. And this same statement should work for, you know, more general immersed spheres and form manifolds, although then there's still a question of more relations here. But the first open case is the big double of the figure 8 knot. So this is known not to be sliced by work of Jae-Chun Cha. But the question is, you know, does it lie in the next order of the Wiki Tower filtration? So, you know, it realizes this interesting expected non-trivial R invariant, but, you know, we don't know if perhaps there's some, you know, geometric trick that can be used to kill this guy. So, in other words, could could a link that bounds in order 7 Wiki Tower, or could this being double of the figure 8 knot also bound in order 7 Wiki Tower? So I should probably stop here. Okay.
Any questions for Rob?
So you decided the length, and is there all defined in this sort of any Whitney tower? Is there all defined element in this group?
Pardon me, you start with the link, and it has it bounds in order in Wiki Tower.
Yeah, I was just wondering, can you show that this is a well-defined element in a group, or do you have to refer to the numbers in there?
Well, so it depends what order. If the order is not equivalent to 2 mod 4, then you just read off the intersection tree, and we don't have a basis written down for any particular order, but you could do it, I guess. I'm not sure, is that what you're asking, or?
Well, I was just wondering, can you move to other manifolds, or if you don't need numbers in there, it's just self-defined, can you define this by order intersections of the element?
Okay, yeah, so I understand now. So for links, we're using Millman invariants. Now we're, you know, working on extending this, so for, you know, for certain examples of 2 spheres and 4 manifolds where you get it by attaching 2 handles to the 4 ball, it's also well defined. But we're, you know, because we can translate it back to the link picture. But yeah, so the ultimate goal is to take immersed spheres in any 4 manifold, build a Whitney tower, compute the intersection tree, and say whether there's some obstruction to, let's say, homotopic spheres to embeddings or